Welcome back to DemystifySci. I'm Anastasia.
I'm Shiloh.
And this is the place where we explore the theories that may change the world. Why do we say may? Because not every single idea that we present on this podcast receives a ringing endorsement from us. But we believe that the intellectual commons demand a place like this, where anyone can come and present an idea, and the only thing that we vet it for is, does it hang together? Are the assumptions good? Is the logic solid? And if it is, maybe it will change the future. And so today, we are very proud to present to you a talk that was given at DemystiCon, which was a conference that we held in Portugal. It's called Beyond the Big Bang, and all of the talks at the conference were about this question of, okay, well, what happens if the Big Bang falls apart? And
Which it seems like it's under a lot of stress right now.
exactly. And so this is quintessentially one of these things, one of these ideas that may change the world, because right now everybody believes in the Big Bang. If alternative theories are sufficiently robust, then perhaps in the future we will live in a steady state universe or something that nobody's even figured out yet. The video that we present to you today is a presentation by Eric Lerner at this conference about how there might be a different story about the formation of the universe that doesn't include expansion. So the current consensus theory is the fact that you have the Big Bang, you have inflation, you have expansion, you have all of these very strange physical dynamics at play in the universe, and the consensus is that you have to have those dynamics to explain the appearance of the modern universe. And so Eric's presentation is about the fact that you can use gravity, nuclear physics, and plasma physics in order to explain the appearance of the universe without having to resort to depending on the Big Bang.
And if you're really into Eric's ideas, go back and check out our recent podcast with him where we sit down for a full 2.5 hours and make sense of Eric's take on cosmology. And in all honesty, I can't give him enough of a shout out because Eric got me personally started on this path when I was a little kid. I found his book called The Big Bang Never Happened in the basement of my library in my small town in Ohio. And it was the first book that I found in the pop physics world that made any freaking sense to me. So I'm not saying Eric has nailed every single aspect of this, but it is a very compelling argument, and I think we should take it seriously.
And if you like what we do, come over to patreon.com/DemystifySci. We collect donations that run as little as 75 cents a week. And if you sign up, that means that you help us never stoop to the low of having to have sponsors and advertisements on this program. So come on over, join us. In return, you get to come to our weekly Sunday salons where we would love to see you, chat with you, and explore your mind with our crew of excellent thinkers.
One more thing. We have a new segment going called Paradigm Drift. We actually recorded a live episode of this, which recently came out at this conference in Portugal. But we're doing it on the internet going forward, unless we find the venue to do it live. What it means is you get to sign up for a chance to present your crazy idea, which may not be crazy at all, but you, the audience, get a chance to talk to the rest of us. And if we like your idea, maybe we'll invite you back to elaborate on it. So you get 60 seconds to do that. And that's a short amount of time to convince anybody of anything. But if you can intrigue us, maybe you can develop it to the full extent of an entire podcast at some point. So check out the link in the description, sign up. The next taping is going to be on August 4th at 7 p.m. Western Pacific time.
And for now, all business is done and laid out, and ahead of us is Eric Lerner's presentation on a universe without the Big Bang.
The scientific revolution starts now.
The DemystifySci podcast.
Let us see in the dark.
What I'm going to be talking about is cosmic evolution without a Big Bang. So this is sort of the quote that guides a lot of my work from Hannes Alfvén. To try and write a grand cosmical drama leads necessarily to myth. To try to let knowledge substitute ignorance in increasingly large regions of space and time is science. So the idea is, instead of, as many of you are trying to do, creating ex nihilo theory of everything, we work outward in space and time, step by step, to develop knowledge of the universe without theoretical preconceptions. So if the Big Bang expanding universe hypothesis is junked, is thrown away, then the evolution of the cosmos can be understood using basic concepts of gravity, nuclear reactions, and plasma physics. In other words, the science that we already know from laboratory experiments, including the laboratory of the solar system that we can now reach with our spacecraft. Imitating these same plasma processes is the way to produce fusion energy on Earth. In addition, what I'm going to be showing is that cosmic evolution can be best understood as an overlapping series of processes. So we're not starting in a reductionist way from atoms to molecules to stars to galaxies and so on, but discussing the processes that sustain these structures and, of course, are modified by them. So the first basic process that people have to understand is the pinch effect. So the pinch effect, although not by that name, was discovered by Faraday 200 years ago. And the question is, can we get any of these things wrong? Okay. So when you have two currents moving in the same direction, they attract. If they're moving in opposite directions, they repel through their magnetic fields. So what this means is that in a plasma, in space, you have a natural tendency of currents to organize themselves. First of all, it's unstable because obviously you have the acceleration of structure formation through these currents, and the currents organize themselves into filaments. Now, in this process, especially in space, you have an additional effect, which is anisotropic conductivity, a magnetized plasma. So what happens is electrons or ions moving in a magnetic field circle around the magnetic field lines. They can only cross the magnetic field lines when they're hit by another particle. So they have a collision. Well, in space, plasmas outside of stars are so undense that the collision rate is insignificant compared with the gyro rate. So that means that electric currents are constrained to go along the magnetic field lines, which the currents create. So what Alfvén and Feldhammer discovered 60 years ago, more, is that that means that a basic organizing structure in the universe is a force-free plasma vortex filaments in which the currents along the outside are almost circular, and they produce fields along the inside, which are straight lines. And the currents that are running along those fields on the inside produce the fields on the outside that those currents run around. And in between, the currents run in helices. So this is something that's been seen millions of times in the laboratory and in the cosmos. So if you take these basic processes and we say, how far back in time can we understand the history of the cosmos? Because we're not saying, oh, we can sort of intuit a beginning, because there is no beginning. But we look back as far as we can. If we look back as far as we can envision a point in the evolution of the universe where there was a hydrogen plasma. So nothing was existing except protons and electrons, and of course, electric and magnetic fields. So this is an animation, not a simulation, of what we can calculate happened in that early time. Let's see. So what we have is the contraction of these initial force-free filaments, because we're running in currents moving in the same direction are organizing themselves and repelling currents moving in the opposite direction. So those are the field lines, and we see basically a hierarchy of currents developing at all scales. So the smallest scale is about 10,000 light years at the density of the universe that we actually observe. And we see in the present day universe these same structures forming like the Veil Nebula. But over immense lengths of time, this is trillions of years, you have the buildup of these filaments into larger and larger structures, which again we can observe in the laboratory on much smaller scales, so that eventually you get to maximal structures, and I'll tell you how we calculate these maximal structures, in which the filaments are of the order of a gigaparsec in radius. So once we get to a certain level, this gigaparsec, then gravity starts to become a significant factor, because in plasmas, we find that velocity is a scale invariant. So the velocity of plasma phenomena of a similar type are the same at all scales from the laboratory up to the largest, which is very convenient because it means that things that take billions of years in the cosmos take microseconds in the laboratory, because time scales as distance when velocity is a constant. But gravity scales in a different way. So gravity is compared with electromagnetism, compared with plasma phenomena, gravity is totally insignificant on laboratory scales, but gets more and more significant with larger and larger scales. So once you get to gigaparsec scales, these two forces come into balance, and therefore you have the possibility of gravitational contraction. Now, in addition, the scale is determined by the fact that for an object to contract, its plasma must be collisional. That means that the average particle will collide with another particle within the dimensions of the object. If it's not collisional, then you have something like the solar system. The solar system is obviously gravitating, but it's not collapsing because it's not collisional. The planets are too far apart at the moment to collide. So what we have approximately of the order of 6 or 7 trillion years ago is that these filaments start to collapse gravitationally. And they start to collapse first along their axis. So basically what we first have is a collapse into disks. And these are rotating disks. And what happens is that you have the formation of these filaments at progressively smaller scales. And this is important because for an object to collapse, it has to get rid of angular momentum and has to transfer angular momentum out of the object. Magnetic fields can do this through these filaments that form at all scales. So we go down in scale from superclusters to galaxies to molecular clouds. always forming these filaments at smaller and smaller scales until we get to the scale of stars. And again, all of these all of these objects can only form because the filaments are effectively transferring angular momentum to the surrounding plasma. And this cannot happen with gravity alone, because gravity cannot transfer angular momentum. Magnetic fields can transfer angular momentum. So you have this whole history that is basically formed simply by the interaction of the known laws of gravitation and electromagnetism through working on plasmas. Now, another process that is involved here is the homopolar generator, or a Faraday disk generator, again going back 200 years. So when you have an object moving in a magnetic field, it generates currents that move towards the center along the perpendicular to the axis, and then go out along the axis and complete the circuit at some remote distance. So that's what's creating these inward going sets of filaments. Now, I should mention, you do see these filaments in the simulations that use purely gravity. But unfortunately, I have to say, this is totally unphysical. There have been a number of papers that show that the filamentation that's shown in conventional cosmic simulations, which ignore the existence of electromagnetism, the filamentation is put in by hand. So there's a thing called artificial viscosity, which is an unphysical term, which is put into the algorithms, because if you don't have that artificial viscosity, you don't get filaments and you don't get structure formation. Without magnetic fields, you can't get structure formation because you can't get rid of that angular momentum. So unfortunately, all these simulations you see that show these webs of filaments forming with only gravitation, those are animations as well. They're not simulations of real physical processes. To get filaments in the real world, you need magnetic fields, which of course we do have. So what is the evidence for this story? Is this just another cosmic myth? Well, first of all, we observe these filaments at all scales. In our laboratory in Middlesex, New Jersey, we produce these filaments at the scale of centimeters. So this is 1 centimeter here. We see these filaments as a vital part of the study of the formation of stars at the scale of molecular star-forming clouds. So this is on the scale of a single parsec. We see them on galactic cluster scales. So these are filaments observed in a cluster of galaxies, and this filament is of the diameter of the Milky Way. The Milky Way is basically the same size as the letter E on this image. And then we see them on the scale of superclusters of galaxies, the filamentary network, the cosmic web. So all of these are basically, what we're seeing is these same force-free filaments. And we see them, for example, JWST has produced these enormously detailed images in the infrared of, this is a nearby galaxy, M74, and you can see the fractal structure of filaments within filaments. In the 1980s, I used these standard formula to show how the numerical structure of the cosmos can be easily predicted simply from the fact that plasma velocities are invariant. And we can actually calculate from plasma physics what these velocities are. So the limiting velocity of these filaments is about m over m. So the ratio of the mass of the proton to the mass of the electron to the 3/4 power times c. So that turns out to be about 1,000 kilometers a second. And there's another limiting velocity, which is about 100 kilometers a second. So velocities at all scales in the universe tend to be in this range. So what you find out that for contracting objects with a given mass, and these lines are lines of constant mass, they go from this line of constant surface density. So this is nr, density times radius, or mass per square centimeter, of 10 to the 19th. So this determines the spacing between objects, and then they go to a limiting gravitationally bound velocity of between 100 and 1,000 kilometers. So this is the dimensions of contracted objects. And you get from this very naturally the marked structure of the universe, that the spacing of objects becomes more and more remote relative to their size as you go down in scale. So our sun is separated by millions of solar radius from the nearest star, but galaxies are separated only by hundreds of radii from the nearest galaxy, and so on up to clusters and superclusters. So all of this has been confirmed quantitatively by measurements of magnetic fields in objects at various size. So this gives the currents, electrical currents that are moving through objects from the intergalactic medium all the way down to a protostellar disk, and the degree of magnetization, which was the degree of that the gyro frequency exceeds the collision frequency. So until you get down to the high density of stars, all of these plasmas are magnetized and are all operating with basically the same processes. Simulations done starting 30 years ago using actual electromagnetic forces, but ignoring gravitation, show that you can get, by electromagnetic processes alone, both the morphology of a spiral galaxy and the flat rotational curve that we observe. It's very important to note that the flat rotational curves that are observed are the rotational curves of the gas, the plasma moving in galaxies, not the stars. The stars are mainly governed by gravitation because they're very high density. But the plasma is governed both by gravitation and magnetic fields. And we can see in our own Milky Way that the velocity of the plasma in the universe, in the galaxy, which is measured through radio waves, that's almost flat and even rises with distance from the center of the galaxy. But the velocity of the stars actually declines. So when we talk about the flat rotation curve, we're only talking about observations that are made in the radio of these gas, not of the stars. And the fact that these two are different is absolute proof that we're looking at something that's governed by both magnetism and gravity. If it was gravity alone, or inertial forces or whatever, these curves, of course, would be identical as Galileo demonstrated. So the mysterious force that is keeping the galaxies rotating at this excessive speeds is the force of magnetism. And as they said in Star Wars, there is a force pervading the entire galaxy, and it's the magnetic field. So if we use these basic laboratory-confirmed processes, we can model the formation of galaxies and the formation of stars. Because what comes out of this, that nr is a constant, means that as the density of plasma in a galaxy increases, the size, the mass of stars that is formed from those plasmas decreases. So we can predict a sequence of formation of stars that starts with the largest stars. And don't have time to go through this in detail, but basically what we find is stars that are massive enough to form supernova and therefore produce heavy metals are confined to a disk. And stars that are from 12 to 4 solar masses are formed in a sequence in the bulk of the galaxy. Now, we don't have an animation for this, but we're about to produce one in the coming month. So what we predict here, and this was predicted back in the 1980s in papers I published, is that in the early stage of a galaxy, the galaxy is dominated by large stars that have very fast fusion burning. So they are about 100 times brighter per unit mass than the sun. And they burn hydrogen to helium far faster. So that's where we get the 24% helium. And again, this was predicted in some detail in papers I published back in the 80s. More recently, we have complete confirmation of this from data from HST and then later JWST, in which we find that extremely bright galaxies, ultraluminous infrared galaxies, have a ratio of their luminosity to their mass that's 100 times that of the sun. So this is, the sun is, solar luminosity is down around this line. And the galaxy is about a factor of 5 lower, our Milky Way galaxy today. So you have the ability of these galaxies with these much larger stars to produce the right amount of helium in only 200 million years. And we did these calculations back in 1989 for deuterium, helium, lithium, beryllium, and boron. And we redid them with better data 5 years ago, and they very much match observation. The processes that produce deuterium, lithium, beryllium, and boron come from the cosmic rays that stars produce that go out into the interstellar medium and produce these light elements by spallation. So actually, deuterium is produced by collisions between protons, and lithium and beryllium and boron are produced by breaking apart heavier nuclei, such as the nuclei of carbon, nitrogen, and oxygen. So we have good agreement with thousands of points of data of helium abundance, lithium abundance, and beryllium abundance. So this is the evolution of these abundances versus the abundance of, for example, oxygen, which we know becomes more abundant as the history of the galaxy proceeds. So out of these thermonuclear processes that are correctly modeled without any dark matter, dark energy, or new physics, we obtain the energy for the cosmic microwave background. Now, this has been known back since the 60s, since the discovery of the cosmic microwave background that if you take the energy that's necessary to produce the helium in the universe, by amazing coincidence, it's equal to the energy of the cosmic microwave background. And that's because the cosmic microwave background's energy comes from the energy of stars. So in these early galaxies, which we now can observe, these early galaxies are so dusty that the stars are basically invisible at visible light, and their light is thermalized down to approximately 20 K by the dust that is enclosing the galaxy as it forms. When the galaxy gets to about 200 million years, the dust has condensed into the disk, and then you can see the stars. So what happens is we get thermal energy thermalized down to about 20 K. Well, how is it thermalized and isotropized all the way down to 2.7 K? What we see in this plasma process is at the center of galaxies, these excuse me, these currents converge and they kink up to form plasmoids. Now, plasmoids we observe routinely in our experiments at our laboratory, which I'll discuss in the afternoon, are self-contained, magnetically confined objects. So the currents moving through the plasmoid create magnetic fields that confine them into a little ball. Instabilities within the plasmoid create beams of ions moving in one direction and electrons moving in the other direction. And this is a very good quantitative model for things like Herbig-Haro objects, active galacti, nuclei, and quasars. You don't need any gravitation to form these objects. So these filaments are quite important because we can predict, again, simply by electromagnetism, that these filaments will form a downward hierarchy of extremely dense magnetic filaments that go out into the universe and have the ability to absorb and re-emit microwave frequency radiation. So you get a microwave fog, which is what isotropizes and thermalizes the cosmic microwave background. And again, for decades, we've had proof that this fog exists, that the universe is not transparent in radio frequencies. Because there's a correlation between the infrared and radio waves produced by ordinary galaxies. It's not a linear correlation, but it's quite a good correlation. And if you look at galaxies in our neighborhood going out to about 600 megaparsecs, so this is too close to us to be accounted for by any sort of cosmic evolution. This is only a billion years ago. What you find is the further you go away from Earth, the less the radio radiation for the same infrared luminosity. And this drops by a big factor. This is a factor of approximately 10. So unless you want to accept that the Earth is in a very exceptional spot, you have to accept that there is absorption going on and re-emission of radio waves into the microwave radiation background. And another proof of that, by the way, is what I mentioned in my earlier presentation, this recent discovery of this 300 trillion electron volt photon. If the density of the cosmic microwave background is linked to the density of matter, then as you go out into space, you have a lower temperature for the cosmic microwave background. We can't see that lower temperature because the temperature around us is 2.7 K, and we're looking at a semi opaque object. So again, from actual observation, this is a much more consistent explanation of the cosmic microwave background than saying that it was produced by this multi-trillion degree fireball long ago. So to sum up, what we have is a universe that is running up, not running down. If we look at the energy flows in the universe, from primordial vortices to superclusters of galaxies, the galaxies to star clusters, there's a correlation between the time of duration of these objects, which gets less and less. This is logarithmic from trillions of years down to star formation rates that take only thousands of years, and the power density, the flux density, watts per centimeter squared. When we get to the thermonuclear stage of evolution, this is main sequence stars. We have this whole curve still existing, but moved upwards by very many magnitudes because fusion reactions are far more energetic than the basic gravitation energy sources that were present in the contraction stage. So this brings us to the present. Right now, as far as we know, the process of evolution in the galaxy has moved furthest into fastest time scales here on Earth. So while the evolution of the galaxy takes billions of years, social evolution on Earth has been increasing energy flows on the scale of centuries and even decades. As I'll describe more in my afternoon session, it is not just cosmology that is in crisis, it's humanity that's in crisis. And this crisis is not just of the present day, but has been developing for some time. If we plot human progress two ways, by the rate of energy increase, the annual rate of energy flows in our society, which is the orange curve, and the rate of mortality decline, so the faster the decline, the better off we are, we find that these curves in the post-war period, post-World War II period, peak in the late 1960s. So the 60s were the good old days. And as we move into the 70s and the end of the post-war boom, there's an enormous decline in the rate of mortality decline and in the rate of energy increase. So there's been a period of near stagnation, slow growth, all the way from 1980 to 2010, somewhat broken in the first decade of the 21st century by the integration of China into the world economy. And now we're in a period in which this decline has gone into actual negative territory. And since the beginning of the pandemic, the rate of energy increase has actually become a rate of energy decrease, and the mortality rate of the world population is now rising. The only way, and again, I'll go into this in the afternoon, we can escape this is with a new source of energy, a denser source of energy, and that's fusion energy. And again, I'll pass off this animation until tomorrow, until this afternoon. But our device, the dense plasma focus device, uses these plasma filaments, which we study in the universe, to compress plasma and to heat it to temperatures more than 100 times that in the center of the sun, which have been reported in peer-reviewed journals. And that's what's producing our fusion energy. Through that process, we expect to produce a megawatt generator. And here we see the filaments forming and forming into a plasmoid. But as I say, I'll skip over this and go into this more in detail in the afternoon. So out of this process, we expect in the near future to demonstrate in the laboratory net energy out of the machine, more fusion out of the machine than we put into the machine. And from there, with a much larger engineering project, develop a 5 megawatt fusion generator, safe, no radioactive waste, compact, much cheaper than any existing energy source, and decentralized. So we are going to be using the knowledge that we gain from studying plasmas in the universe over the past half century to produce the next stage in human evolution. To understand fusion energy, we need to understand and imitate the processes that drive cosmic evolution. And this can be only done in the context of cosmology studying trillions of years, and therefore cosmology without a Big Bang. Thank you.
Remember, questions first, comments second.
John Place, Fiat Luke's blog, Thoughts about the History of Science. Thank you very much for your presentation. I remember reading your book when it was published, and I still remember passages almost word by word. You showed the plasmoid, and in your book, when you're in this section referring to the different scales of cosmic plasma and how they scale down using the work of Alfvén and Faltheimer, you get in the laboratory centimeter size plasma, which are whose activities take place in nanoseconds, corresponding to cosmic plasma, taking eons. You mentioned Bostic's work on plasmoid, and I was wondering if further work has been done on the shall we call it plasma at the microscale, such as the work of Bostic.
Right. Well, yeah, that's what we're doing. In other words, first of all, let me just run the video the animation that I skipped over, which shows the formation of plasmoids at the galactic scale. So basically, what we're saying is these are produced along the axis of the galaxy. And this is what we see as, the quasar, the Herbig-Haro object, the active galactic nuclei. So these, as we observe in nature, these have tremendous magnetic fields. Now, they're fairly massive objects, but there's no evidence that they actually have confinement speeds that approach the speed of light, which, by the way, the formation of black holes was viewed as impossible by Einstein and other pioneers. It was Einstein demonstrated that you couldn't get, although you could get relativistic velocities, you could not get to a black hole condition. And Oppenheimer demonstrated that if you could get to a black hole condition, it would take an infinite amount of time. And when I've pointed this out to black hole cosmologists at conferences, they say, oh, that's in the Earth's frame of reference. We're talking about the frame of reference of somebody falling into the black hole. Then the black hole will contract in a finite amount of time. So this is another way of saying black holes don't exist. So what does exist is these plasmoids. They certainly are massive, but they also have enormous magnetic fields these magnetic fields depend on their scale. The larger the scale, the smaller the magnetic field, although the larger the currents involved. So we study, and about 40 other groups that use the same device, the plasma focus, we study the formation of these plasmoids at an extremely micro scale. These plasmoids are typically about 300 to 500 microns in radius. And to get fusion at a net energy level, we have to compress them more optimally so they get down to the scale of only 30 microns. That's what we're aiming for. So we study these, and as again, we'll go into this in the afternoon, with fast ICCD cameras, which have exposure times down to about a fifth of a nanosecond. So we can capture these plasmoids, and I'll show you examples of them in the afternoon. So there has been enormous progress in studying these for the very practical reason that these plasmoids are what we believe to be the fastest route to getting economically viable fusion energy.
Excellent. Thank you.
Thanks. I like to try to clarify what can we see as opposed to what is derived from theory or observation. And it sounded like you were showing that there are two types of galaxies that we can see, the radio galaxy and then the infrared and visual, and that they rotate at different rates.
No, these are not two types of galaxies. These are two components of galaxies. So the inner part of a galaxy, the part of the galaxy that we can see in optical and infrared, that's the light that's coming from stars. Now, stars are these very dense objects. And I did forget an important point, which is when we go to stars, we no longer have magnetization. Stars are so dense that they're collisional. So these filaments don't form in the same way within stars. So you don't have we don't have the hierarchy of structure going down lower than stars. I mean, we do have the same process producing smaller objects, which are planets, but within the stars, there's not the same hierarchy because the plasma is now collisional. So these stars are producing the beautiful pictures of the spiral galaxies that we see in the optical. But when astronomers trace these rotation curves outward, they are not using optical data. The observations are radio wave data. The radio waves are coming from the emission of plasma. So if you go further out in radius in any galaxy, we're talking about disk galaxies, not the ellipticals, then you have fewer and fewer stars, and so few stars that you can't use light to measure the velocity. That's why the radio waves are used. But that's only measuring the velocity of the gas. So what you have is the gas is moving supersonically past the stars. If there was only gravitation, that would be impossible. After Galileo, we know that objects of different densities move identically in a gravitational field. So you would not have a situation where stars and gas are moving at different velocities. But that's what we do observe. And that means that the gas must be confined additionally to the gravitational attraction by the magnetic fields. And this is simply ignored because one of the big flaws of conventional cosmology is they ignore the existence of magnetic fields.
Thanks, Aaron.
Thank you for an interesting talk, Mr. Lerner. At one point, you had said something about the distances, and I think it was something along the lines, and correct me, I probably wrote this down wrong. The mass of the proton divided by the mass of the electron to the 3/4 power times c. Did I write that upside down?
I think I set it upside down.
Okay, no, because
So it's the mass of the electron divided by the mass of the proton to the 3/4 power. So that ratio is one of these numbers that we all scratch our heads about. Where did that come from? But that's 1836, 1836 point so on. And then if you take that to the 3/4 power and multiply it by the speed of light, you get a little above 1,000 kilometers a second. And roughly speaking, that's a speed limit of most plasma in the universe. In the densest clusters of galaxies, you can get above that by roughly a factor of 2. And then the lower limit is the simpler ratio, which is the
because that actually comes out to be the Rydberg speed. So I say that's why I asked, because one was like 280 times the speed of light. Well, that doesn't really make sense. Just 1 over that and inverted.
Right, it's
it was
1
very
over
good agreement.
1/280th the speed of light. And then the lower limit is the electron mass divided by the proton mass times the speed of light. So that is of the order of a little above 100 kilometers per second, 150.
All right, that makes sense.
So I'd like to point out like a couple of sort of observations regarding the missing gravity problem in galaxies, this so-called flat outer rotation curves. Number one, we have dwarf galaxies as well, satellites of the Milky Way, but also field dwarfs, which are very poor in gas. They're mostly stars. They're also not rotating. They're supported by the random motions of the stars. So kind of like an elliptical galaxy. In fact, these are, if you like, dwarf elliptical galaxies. And the velocity dispersions in them are often much higher than you would get from applying Newtonian dynamics to the stars that we can see in them. So there is missing gravity also in these non-rotating gas-poor systems, quite different to the rotating spiral galaxies like the Milky Way. So that's one thing. The other thing I'd like to point out is the gravity between the Milky Way and Andromeda galaxies must have been enough to turn their expansion around. And I don't know how you can, whether you can account for that, because there isn't. You're proposing that gravity is Newtonian, but there wouldn't be any long-range magnetic forces between them.
Well, I mean, the long and short of it is that, yeah, I haven't done any particular studies of the local group. The key point is that the vast majority of data on which is based the idea that dark matter has astronomical evidence for it. We're all agreed that there is enormous evidence against dark matter from the laboratory. But the idea that dark matter really has to exist and is not just a fudge comes from these rotation curves. That's the overwhelming amount of data. And what I'm saying is that data is overwhelmingly based on measurements of the motion of gas or plasma.
It's not entirely from the gas, though. I mean, if you also look at the orbital velocities of satellites around the Milky Way, and these are satellites which are mostly made of stars, or pretty much entirely made of stars, you can see the rotation curve of the Milky Way, for example, at 100 kiloparsec or 150 kiloparsec, is approximately the same as the velocity at which the sun orbits around the galactic center. So it is true that astronomers generally consider the measurements based on the gas to be kind of more reliable. But there are data on the rotation speeds from stars as well, and they do show a flat rotation curve as well.
Right, but the question is, if you go out to larger and larger scales, then you have to take into account what is the actual balance between magnetic energy and gravitational energy.
I was just talking about the observations.
And in what?
I was just talking about the observed rotation speeds.
Yeah, let me finish my answer, okay? What you have at many scales is that the controlling forces, the dominant energy, or at least equal energy, is in the form of magnetic fields. Those magnetic fields act directly on gas clouds. In many cases, those gas clouds are enormously more massive than the stars within them. So the motion of those gas clouds is controlled by both gravitation and magnetic field, and the stars within them are gravitationally bound to the gas clouds. So you can have the motion of stars indirectly controlled by the magnetic field. In a galaxy like the Milky Way, the stars in the inner part of the galaxy, where we're measuring velocities optically, the density of matter is too high for the magnetic fields to be controlling. A technical way of putting this is that the Alfvén velocity, which indicates how much energy you have in the magnetic field, is much lower than the actual velocity. But on many scales, and some even at the level of clusters of galaxies, that's not true. The Alfvén velocity exceeds the kinetic velocity, and there you have magnetic forces are powerful enough to control the motion of the clouds that the stars are embedded in. So you can have magnetic fields indirectly
So if I can,
controlling the mass of the clouds. By the way, the concept of mass density is quite critical to the behavior of these plasmas. And the graph I showed you, which was theoretically derived, gives a prediction for the mass density of the universe at large scales. And that prediction is very close to the observations of actual matter at these scales. One of the problems I have with the theories of some of my colleagues here is that they assume that the density of matter in the universe is the so-called closure density. And that closure density is about 100 times the density we actually observe.
So one thing I wanted to ask is regarding the gravitational lensing of galaxies. So galaxies also lens light from background galaxies more than is expected from applying sort of Newtonian gravity, general relativity to the visible mass. So do you understand how that's possible?
Well, you know, as I say, at the scale of galaxies, you can explain most of these phenomena simply by adding the magnetic fields. In the case of clusters of galaxies, where the most direct measurement of the mass is the mass necessary to contain the plasma that's giving off the X-rays. So again, first of all, determining that mass depends on what you think the structure of the gas is. If the gas is extremely inhomogeneous, it's going to produce a lot more X-rays than if it's homogeneous. Or conversely, you can get a same amount of X-rays with a smaller mass if it's inhomogeneous.
Sure, but I was asking about the gravitational.
Excuse me.
Okay.
You got to let me finish, Earl. So there's uncertainty of how much mass is confined by the magnetic field. I think that clearly you have that the evidence is that in the biggest clusters of galaxies, there's about a factor of 2 or 3 between the mass that we can see and the mass evident from the gravitational field, either measured by lensing or by X-rays. So
I have
whether that but that discrepancy can be described as dim matter. It isn't at all evidence for non-baryonic matter, because that assumes that we can see all the matter that's there.
I think
That's simply not true.
There's a really interesting feature of lensing that Ed Dowdy did some work on, where he was showing that lensing around the sun behaves in kind of a strange way that I think might be relevant to this. And so I want to have one more question in this session before we go to the coffee break, but I'll hopefully have a chance to talk to both of you.
I do want to, there is one other thing about lensing that people should be aware of, is that the lensing that people talk about is the strong lensing from the center of these clusters. And there is a degree of extrapolation to go out to the outside, because it's basically assumed that the ratio of total matter to the matter that we observe continues outward. And there are a number of good papers that show that that's just not the case, and therefore that the unseen matter that is assumed in the inner parts of the galactic clusters doesn't necessarily have to be present on the outside. And in fact, if you assume it is, you get contradictions to other observations of the interaction of the cluster with other clusters.
Hi, Eric. Chris Lato. I make videos on fractal universe, among other things, on YouTube. And you mentioned scale invariance. You mentioned there's fractal patterns. You mentioned condensed matter. Did you note any periodicities or patterns? And were you able to fit any sort of fractal function or look into that?
Right. Well, yeah. So Chris had, I guess, independently of reading my papers, noticed the same regularity that the spacing between objects is governed by m over r squared, or n r equals a constant. And yeah, these regularities, the two regularities of condensed objects and the distance between these objects, they've been noticed pretty far back. I certainly wasn't the first one to notice them. Certainly 50, I started studying this in the late 70s. So it was before then, 60s or 70s. And my contribution was I put that together with Alfvén's theories of cosmic evolution and showed that you could derive from plasma theory not only that these scaling laws should exist, but what the numerical values of the scaling constants are. So this is something that many people have been studying independently for quite some time. And I haven't been giving references, but we can all communicate with each other by email, right?
Like the whole conference, or just us?
Are you going to distribute the emails?
Well, I can if people would like us to. I think
if people give permission, I think that it would be good.
Sure.
Because then I could send out, a reference list to people, and then they can look at these papers themselves.
Yeah, we can organize something like
Patrick has ideas, but we can put together a page on our website too and link everybody who attended and stuff like that. We'll figure something out.